Alright, so I'm recording. So today what we are going to be talking about are the gas laws. Now the last unit we talked about the behavior, but that was very qualitative. That was just using like quicker, slower, what kind of speed did they have, but we never really dealt with numbers. That's what we're going to be talking about here in this section. We're going to be talking about how to calculate the volume, pressure, temperature, all of that jazz based off of the other variables. Okay? So, to get us started, there are a couple definitions that you need to know. Okay? The first one is standard temperature. If I'm saying find something at standard temperature, I'm referring to 0 degrees Celsius or 273 Kelvin. Okay? So, anytime I ask you for that, that's the number that that's the magic number that I'm looking for. The same with standard pressure. I'm talking about 1 atmosphere or 101.3 kilopascals. Remember, kilo is 10 to the third, so it's 101.3 times 10 to the third pascals, or just kilopascals. Okay? The last two things deal with, they're just plain vocabulary, like usual words that I might use. So if I ever talk about compression, say that, okay, so I have my volume and I'm going to compress it to a smaller size. What I'm saying is that I am decreasing the volume versus expansion, which is just saying that I am increasing the volume. Alrighty then, so make sure that you're familiar with these words. The next thing there's a couple rules that you have to abide by, okay, in order to use these equations. The first thing and the most important thing is that your temperature needs to be in Kelvin. It's not okay to have it in Celsius because in Celsius you actually can obtain a temperature of 0 degrees Celsius. And if you have a temperature of 0 degrees Celsius, then that'll mess up your math. Because if you plug in a 0 for your temperature, your whole equation is just going to be 0. And that's not true because it's not like you have 0 volume and it's not like you have 0 particles in there. You have a given amount. Okay? So I just wrote up the equation just to reiterate that in order to figure out the temperature of Kelvin, it's just 273 plus whatever temperature it is in Celsius. Okay, that's why it's TC. However, pressure and volume, not so much. They can go back and forth between the different ones. So for volume, it can be expressed in liters, centimeters cubed. Now what I mean by any variation thereof, I'm just saying instead of centimeters cubed, maybe meters cubed or decimeters cubed. Any of those would work as well. It just needs to be cubed. Pressure can be expressed in atmospheres or kilopascals. The one important conversion that you need to know is that for every 1 atmosphere is equal to 101.3 kilopascals. Okay? So anytime, you can use these just like you're going from inches to foot, feet to yards, the same thing. I might give you it in atmospheres, but I want to know it in kilopascals. And so you would use this conversion factor in order to figure that out. Okay? Just normal dimensional analysis, nothing too stressful. The last thing is just to make sure that you keep track of your units, because there will be a lot of, each variable has its own specific unit, so you want to make sure that your end result is in the correct units, that if you are talking about pressure, that you're ending in pascals or atmospheres, and you're not getting some answer that's centimeters cubed. If you have an answer to centimeters cubed, you did something wrong, okay? So make sure that you keep all of those straight. Alrighty then, so the first law that we're going to be talking about is Boyle's law. Now Boyle's law is just is an expression of the volume, or it's just trying to figure out the volume of a given amount held at constant temperature, which varies inversely with pressure. So it's just the relationship between pressure and volume, okay? And it's expressed in this equation right here. Now let me ask you this, based off of this equation, an increase in volume would cause a what? Increase or decrease in pressure? What do you think?
An increase in volume would what?
Increase the pressure.
It would what?
Decrease.
I think it would decrease because there's more space.
It would. Oh, that's a good. Yes, that's a good way to think about it. Think about it in terms of space. That's good.
Okay, I was like,
It would decrease the pressure. Okay? Remember that I said that it is an inverse relationship. So as one goes up, the other goes down, or vice versa. Okay? So go ahead, write down the question. Alright then, so let's go ahead and do the problem. So like I said, I always label it P1, V1, all of that, all my values. Okay? So P1 is equal to what, guys? Very good. 210 kilopascals. Okay? V1 is equal to 4 liters. P2, well, we don't know what that is. And then V2 is equal to 2.5 liters. All right? Now remember, in order to use this equation, you have to have a constant temperature. If there is any variation in temperature, you cannot use this equation. Okay? So the moment that you see any variation in temperature, this one becomes null. You can't use it. All right? However, because there is no variation in temperature, we can go ahead and use Boyle's law. P1 V1 equals P2 V2. Okay? So let me go ahead and erase this. All right? So in this case, it's going to be 210 kilopascals. Now, I write out all of the variables because I want to make sure that the correct units cancel out. So if I can write it out, you can too. Equals 2.5 liters. And then I'm just going to put X as my variable. You can put however pleases you if you want to keep it as V2. Or I'm sorry, P2. That's cool too. But I usually keep it as X. So then what do? You just solve for X. So X is equal to 210 kilopascals times 4 liters.
Is that to the... Wait, is 2.5 liters to the X power? Or...
Right, so 4 liters, divide that by 2.5 liters. Now the cool thing about units is that you actually can treat them like numbers, okay? So if you had a 2 on top and a 2 on bottom, what would you do? You would cross them out, correct? Very good, because it would act just like a 1. So the cool thing is that you can do the same thing for variables. Do you see, or I'm sorry, for units. Do you see what we can cancel out? Very good, the liters. The liters cancel out. So, I didn't mean to do that. But the thing is that I am just canceling out the liters part of it. I'm not canceling out the number. Did I cross out the 2.5 or the 4?
So
No.
like the T-chart kind of? That
Yes,
kind of-
exactly.
Okay.
Exactly. It's just like the T-chart. So, what do you call it? And then you just solve. And I know I did it right because the only variable that's left is a pressure variable. Now, can I ask you before we answer it, do you expect the pressure to be bigger or do you expect it to be smaller?
Bigger. Smaller.
All right, well, look at what's happening to my volume. Is my volume increasing or decreasing?
Decreasing.
So if it's decreasing and I have an inverse relationship, what would you expect it to do?
Increase.
Very good, to increase. This is a good way to check your number. Now, it won't tell you if the number is correct, but it will tell you if you are on the right track, or it will tell you definitely if you're wrong. Because if you ended up with a number that was less than 210, then you probably did something wrong, because you should expect a number that is bigger. So can anyone tell me what that number is? Very good, 336. And then what are the units? In kilopascals. Actually, I would like you to do that. Instead of saying X, keep it as like P2. So that way you know at the end that it's the pressure 2 is equal to 336 kilopascals. So yeah, make sure you keep whatever variable was in place. So this shouldn't be X. This should be P2. Okay? So that's how you do it. Simple math, I promise. It's not like stoichiometry. It's really chill. Okay? Alright, so the last one that we're going to talk about is Charles's law. Okay, so that expresses the direct relationship between the volume of gas and temperature at a constant pressure. So now this time, my pressure doesn't change. As I go from one condition to another, the pressure stays the same. So that's why we're able to just focus on the volume and the temperature. Okay? And so if it's a direct relationship, if my volume increases, what do you expect to happen with my temperature? What'd you say? You would actually expect it to increase.
Yeah, this one probably stays the same.
Mm-hmm. So this one is a direct relationship. So as one goes up, so does the other. Okay? Alright, so after you wrote down this problem, let's go ahead and solve it. My little handy dandy whiteboard. So like I said, write it out. So V1 was equal to 2.32. T1 was equal to 40 degrees Celsius. V2, well, we didn't know what V2 is. That's what we're solving for. And then T2, well, that equals to 75 degrees Celsius. So what's the first thing that we need to do?
Divide them.
Temperatures.
Very good. Remember, I told you your temperatures aren't in Celsius. They need to be in Kelvin. So we need to convert that first. So 40 plus what in order to turn it into Kelvin? 273. So my new temperature is now going to be 313 Kelvin. And then my other new temperature is going to be what? Very good. 348 Kelvin. Alrighty. Now we're ready to plug it into the equation. And so my equation was V1 over T1 equals V2 over T2. Okay? So we have all that, so we're just going to go ahead and plug it in. Make sure you keep track of all of your units. Alright, and so you're just going to multiply both sides by 348. So that's going to look like this. So 2.32. No. And so as you can see, the kelvins cancel out and you're left with 2.58 liters, which makes sense because as you can see, your temperatures are increasing, so you would expect your liters to increase as well.